All right. Calling your attention to the course calendar. We are just about to the midpoint of this term because we're in week 5. I'm lecturing on assignment number 6 today. You're going to do a drawing, a very simple drawing. You get today and Thursday to work on it, to get it in. And then next week, we're going to do a 3D solid model of a gear, and then you're going to 3D print it. Who in this room has not taken Cadd 199D or Cadd 105?
I'm sitting on my. I'm in it now.
Are you in it now?
Yeah, we're in
Being
it
in it now is fine, because you're learning how to 3D print, which means that you can set your own prints up. I don't have to do all of it for you. But if you need assistance, I'd be more than happy to do that. And I'll talk more about that in detail next week. And then we're going on. Now I'm thinking about modifying the schedule with this assignment here. The gearbox assembly, I may drop that out and we may do something else, because this is kind of just a lot more drawing, and everybody's getting more stressed out with all the work that you have to do. Or I'll just ignore it and just pile it onto you, because it's my last term anyway. But I don't want to work that hard either. And that's where we are headed. All right. So I've got my little mechanisms DVD that's kind of interesting. We've progressed from V-belts, flat belts and V-belts, which transmit power from a motor to some kind of a device. They're good for certain circumstances. They're not so good in other circumstances. Wet environments are one where they tend to slip. The belt stretches, and if you can't adjust it, you get some slippage and some squeaking and things like that. So we go to a little more positive application of transferring power from an electric motor to a device with sprockets and chains, which you've been working on. And then we progress to even more of a positive transfer between a motor and a device in gears. Gears have some formulas that are used to generate information for a machinist that would then use special tools to cut the gear out of blanks. If you've never seen one cut, I think there's some YouTube videos on there that show how gears are cut. It's kind of interesting. I'm not going to show them in here. So we'll take a look at a couple examples. They can be classified as spur gears or pinion gears. Usually the spur gear is larger in diameter and has more teeth, and the pinion gear is generally a smaller one and has less teeth in its use. So for a generalized definition, that would probably be referred to as a spur gear, and this would be referred to as a pinion. But not necessarily true. You'll find different types of applications. The thing about it is that spur gears are two wheels fixed to rotating shafts. The teeth of each gear mesh together to transmit rotary motion and torque, which is part of a design process. And then when we get into shafts, they define the mechanical connection, interestingly enough, as grub screws or keys and keyways. Many parts of mechanisms and machines are connected together using shafts. These are often straight, cylindrical, and made from metal. Several ways of holding pulleys, gears, sprockets onto a shaft. You would probably see that more commonly defined as a set screw. Phillips head, slotted, hex, headed set screw. It's basically a mechanical connection between the two. A lot of times there's a little flat spot that's machined off or just filed off, ground off. in order for the set screw that basically has a flat bottom to have more holding connection, more surface connection, rather than the radius of the shaft itself. And that's the mechanical connection in that regard. And then, if you recall your work in intermediate AutoCAD, or intermediate drafting in winter term, we used a gib head, which is kind of a wedge-shaped key. The textbook and also this little DVD refers to the slot that's in the shaft as being a keyway. I prefer to call that a key seat because the key actually sits in that slot in the shaft, and then the keyway to me is more defined as the slot that goes into the gear, the pulley, the sprocket, potentially to hold those. But it's a mechanical connection that holds the two of them together. Here's an example of what appears to be a give head or a wedge-shaped key that goes into the slot. So that'd be the key seat, and into this would be a keyway to hold that together. There's sometimes even a more efficient mechanism to holding together, and that's using a spline shaft. Interlocking splines machined into the shaft and the hole in the gear wheel. It's going to cost more money, but you're going to have a much more positive connection. Keys tend to, in the design, you want the key to be the weakest part of the design in order for the key to break rather than the shaft or the gear, the pulley, because they're much harder and more difficult to replace. Key is basically you just put a new one in. They can be an interference fit with the hole in the pulley of the shaft made slightly too small for the shaft. When the two parts are pressed together, the friction between them holds them firmly in place. And there are cotter pins that sometimes are also used. Now you have a rotating shaft, and that has to be supported. You did a little bit of that in the centrifugal fan assembly. There were some pillow blocks bearings that were on the fan itself, which held the shaft of the fan. Bearings are used to give the support. And sometimes there are couplings that are used to connect shafts together. So look at the bearings. Bearings are used to support rotating shafts, and they may have to deal with one or two types of load. The radial load is load caused by the shaft rotating itself. And then there's an axial load, which means that the shaft might be trying to move horizontally along its axis, and the bearing has to be able to resist that. There's a lot of definitions of plain bearings. This one has a little collar on the end of it. That would resist the force of the shaft trying to push that bearing through the material that's supposedly trying to give it its lubrication and keep it from overheating and causing problems. They're made from materials that will slide well against each other so that friction is kept to a minimum. Plain bearings could have a little collar on it. If it's got a little collar, it's sometimes referred to as a thrust bearing, or they may have no collar on it at all. And I'll take a look at the materials here. So you've got different types of material. White metal, an alloy of tin and with copper and antimony. Soft and molds itself to the shape of the shaft. If the bearing becomes overheated, it melts and runs, leaving the shaft undamaged. This type of bearing has limited load carrying capacity. Bronze, which is pretty frequently used. An alloy of primarily copper and tin. Phosphorus is added to produce phosphorus bronze, commonly used for bearings. And if you think back to one of the assignments, there was a phosphorus bronze. I think that was advanced drafting, actually, not this class. Cast iron used to form flat or sliding bearings, commonly found on machine tools. Nylon and sintered bearings. Sintered bearings are bushings made from oil-soaked powder of copper, tin, and graphite. Compression molded into shape when hot. Or sometimes the bronze bushings will have little voids in it. And the idea is then to force lubricant into that bronze material to give a quote-unquote lifetime lubrication factor, thinking that lubrication will be internalized enough in that material that it would never run out. Of course, it probably will, you know. I mean, But that's kind of the theory behind it all. And there's also other kinds of lubrication that are involved in keeping things cool and smooth running. There are times when things are just too large, or the shaft itself is not a straight through kind of a situation, like an engine crankshaft that tends to, have little right angle applications to it. Then you talk about using a split bearing. So this is a really large bearing that comes in two different pieces. If you've ever torn an engine apart, we used to do that all the time. Now it's not quite so easy as it used to be. You've got your pistons and your connecting rods, and they have split bearings on them. This is a little oil reservoir in here that's filled with oil that trickles down into that bushing, into that bearing, and gives the lubrication. And then there's also ball bearings. I know YouTube has a pretty good little video on how it's made, about how bearings are made. I believe I showed it in drafting orientation class that I had in the fall. So the outer race is firmly fixed to the component. The inner race is firmly fixed to the shaft. Ball bearings are usually lubricated using grease. And again, if you've ever done a front wheel pack on front wheel bearings, you basically just take a bunch of grease in your hands and shove it in and put it back in. That's basically what we used to do. Friction occurs between shafts and bearings due to them rubbing against each other. Heat's produced, and moving parts can quickly become worn. So the aim is to separate moving parts, so stopping them from touching each other and keeping them relatively cool. Oil and grease are used. Thin oils with a low viscosity, which has a viscosity is resistance to flow. Easily penetrate small spaces and are used on things such as sewing machines. And thicker oils have a higher viscosity, are less easily squeezed out from between moving parts of machines, and suitable for such applications as car gearboxes. Engines have reservoirs of oil, and pumps to circulate the oil in order to coat the moving parts. And other types of bearings have oil cups, which use gravity usually to feed them. All right, so it depends on your speed ratio. Remember speed ratio from our previous two projects? Taking the larger RPM number and dividing it by the smaller RPM number to get a speed ratio. In this instance here, there's 20 teeth and 20 teeth on the gear. We'll put a little rotating symbol on, and we'll put it in motion. They're going to spin at the same speed, and they're going to spin in opposite directions. That's a simple drivetrain of gears. Stop that guy. Go back. So here's a simple gear train. Our old farm equipment that we have pictures of with a motor, and basically spur gear and pinion gear would be a fairly typical definition of those, and rotating in opposite directions. All right, the measure of how much the speed or power is changed by a gear train is called the gear ratio, or the speed ratio, equal to the number of teeth on the driver gear divided by the number of teeth on the driven gear. Simple gear trains, they're spinning in opposite directions. If you need the motor and the device to spin in the same direction, then you're going to add in what's called an idler gear. Insert it in between the driver and driven. And then we can see that they are both spinning in the same direction. And if we need to change the speed ratio, then we're going to change the number of teeth. This is basically 1-to-1. So let's bring this guy down to like 10. We have a 2-to-1 ratio. So the small pinion gear would be spinning twice as fast as the other. And then if we change this, the number of teeth in our idler gear, we're going to change the ratio again. So then we have a little more complicated calculation involved with that. back and look at a compound gear train. Compound gear trains involve several pairs of meshing gears used where large speed changes are required or to get different outputs moving at different speeds. Center lathes, metalworking machinery uses that a lot. And then it has a lead screw on it that will actually move that carriage back and forth, and that's involved in it as well. So we'll take a look at the center lathe video that has a number of gears that are rotating as a compound. Yes?
How does a gear drive compare with a belt drive?
A gear drive is going to be more expensive, but it's going to have a much more positive result of transmitting power from the motor to the device itself. It's going to be more durable. You're not going to, the only change would come is over a long period of time that there would be wear on the gears themselves, but they're usually made out of a very hardened material, and you have a lot more longevity. But it just depends on what the design is going to be, which one is going to offer the best result. And then here's compound gears. Gear trains often have 2 or more gears mounted on the same shaft. A good example of this is a car gearbox, which has to fit into a confined space, has to allow the driver to select various gear ratios, and also has to change from forward to reverse. That would be a manual transmission, for those of you that have never experienced the joy of getting to shift a car, which is a lot of fun. The car I learned to drive on was my mom's Volkswagen, and it was a lot of fun. It was a manual transmission. So you have a lever and you can change the speeds quickly in a confined space. It was interesting because when I taught both my daughters how to drive, and I wanted them to learn how to drive manual transmissions. Because if you get faced with a manual transmission and you don't know how to work it, you're stuck. Anybody can drive an automatic transmission. Well, at one point, one of my daughters was at an event, and the only car that was available was a manual transmission, and none of her classmates knew how to drive it. So she got in and drove it because dear old dad taught her how to drive a manual transmission. And I digress, I'm sorry.
But she stole it a few times, so.
No, they did really well.
Oh, really? That's
Yeah.
cool.
They had a good teacher. All right, then there's bevel gears. If any of you have a grandfather or a father that has one of these drills in the garage, you're all ready for the apocalypse. Did you get the word right? Or the great earthquake, whatever. The big one. Cascadia, whatever. Then you can manually drill holes that you need to, and you're going to make use of the fact that you have bevel gears. Like worm and worm wheels, transmit torque and rotary motion through 90 degrees. So the gear train is basically shafts that are parallel and horizontal or vertical. This has 2 vertical shafts that are at 90 degrees. The rotary velocity of the output gear shaft can be increased or reduced by using different sized gears. And you'll see the results of this, that you can, one gear has a very large spinning effect. So your handle has the larger gear on it, so you don't have to, you can do this, and the drill bit itself, which has to spin at a much higher velocity, is able to do the drilling.
I feel like
Got one in the garage that my dad had.
those weird like penny stamps where you put a penny in and it flattens it and like puts a picture on it.
Yeah.
Okay,
I feel like those penny stamps have one of those.
they might. Yeah.
It has a handle that you
Like
crank.
at Tillamook Cheese Factory.
Yeah.
Yeah. Uh-huh.
Yeah, you give it like a quarter crank or whatever, and like there's a bunch of little gears and
Right,
turns it into
right. Same kind of thought process. So you're spinning this, and that's rotating at a much faster RPM, so that you can actually do drilling, and it really does work. And you're all set for the power grid to go down. All right, bevel gears are found in car differential gearboxes. They allow torque and rotary motion to be transmitted through 90 degrees from the propeller shaft through to the back axles in order to drive the car forwards. So whoever thought of it? I mean, where'd they come up with it? Hey, we want to have a horizontal drive shaft and we want to, go 90 degrees to drive the wheels of the car. It's amazing.
I saw a great video actually describing that. It was like from the 50s, black and white, but it shows just using spokes and pegs.
Oh, yeah, I saw that video. That was a really good video.
Well,
I
Da
think back in the
Vinci,
30s, actually.
Da Vinci, some of his inventions had little dowel pins
Right.
in his cranks and they work, So it's brilliant people that go, hey, I think I'll try something. Inventors, I guess
I
that's.
saw the inside of an old grist mill one time, it was still operating, it was done that way, but the pegs were like about this thick.
Yeah, right.
And it was this big, huge thing, but it was still turning with the water wheel.
Oh, yeah, yeah. Using, forces of nature to help you do your work. So here's this is actually a little scale model of a car that's got a lot of cutaways in it that works really good for demonstrating gears. So you've got your bevel gears in there, transmitting. So the race car drivers always change the ratios in here in the gearbox. Miter gears are meshed bevel gears of the same size and with the same number of teeth. They transmit torque and rotary motion through 90 degrees without any increase or reduction in rotary velocity. Photo below shows bevel gears with helical teeth taken from a motorbike engine. And it's a little quieter. There'll be a couple more examples here. We'll get to that. So miter gears work in pairs. They're bevel gears of equal size with the same number of teeth. Miter gears transmit rotary motion and torque through 90 degrees without producing any change in rotary velocity. So again, if you got one of these in the garage from your grandparents or your dad or whatever, or mom, you're all ready for the power grid to go down and you can grind your own coffee. And they probably have them at, these fancy coffee places anymore, coffee grinders, because that's the ultimate. Yeah. So just the same velocity. And again, just, using physics and making life easier. All right, rack and pinion, the ultimate in sports car design back in the 50s or so. I have a car with rack and pinion steering, which is better than the worm gearing that we'll look at in just a minute. Rack and pinion transforms rotary motion into linear motion and vice versa. Pinion is a round spur gear fixed to a shaft. The rack is a spur gear with teeth set in a straight line. An example right in front of you is our camera tripod that I'm videoing with. Has a rack and pinion for the height adjustment. Drill presses use rack and pinion in the mechanism to move the head up and down for drilling purposes. Rotary motion into linear motion. And this is a little arbor press here that has a rack and pinion where you can place a lot of pressure on something. You can make coins, whatever.
What kind of, like on a vice grip, that wouldn't, like on table vice, the big screw,
Cable?
a table vice.
Oh, a table vise?
Yeah, what kind of, it looks like it's got little screws on the shaft, and then you crank the shaft, and then,
Are you talking about like a vise that's on a bench that you can
Yes.
tighten it, but then you loosen it a little bit and you can basically slide it out? Is that
Yeah,
what you're kind of talking about?
yes.
That's like a square or an Acme thread
Oh, okay.
that's used for that. It's not really rack and pinion. And then there's something internally in that mechanism when you back it off that something opens up a little bit and you can slide that out and slide it in.
Okay.
I don't remember what the mechanism is inside, but Yeah.
So these are also like very.
My old wood shop, they-
Right
Let's just
click,
play with
you just
the
go
bench
straight.
press yesterday.
And then there's another example of rack and pinion that can overcome other kinds of forces, like opening a sluice gate to do irrigation or a dam type of a situation. It is used, raising and lowering. And, oh yes, we might as well put this guy in motion. So once we get to the end, then we come back and we have that linear and rotary motion connection. All right, worm gears are used when large speed reductions are required. The worm, which is attached to the driver shaft, has one tooth and takes the form of a screw thread. Like bevel gears, a worm and worm wheel transmit torque and rotary motion through 90 degrees. So you've got car steering, which is generally that type of a situation. Essentially, although you've got power steering now to assist all of that. And then the ultimate was the rack and pinion, which had a lot more control and was, kind of the ultimate. So here's your little scale model that we've been looking at pieces and parts of, which is kind of cool.
I mean, it looked a lot bigger until they showed us.
Yeah, it looks a lot bigger until you see the hand come in there from the Jolly Green Giant. Okay, yeah, we'll get one more back. Yeah, it's pretty small, actually.
Is that how a real steering wheel works?
A what?
A real steering wheel.
Yeah, it probably it's a little more changed than that, but probably essentially the mechanism. Now this one doesn't really show because this motor isn't really spinning very fast, but generally this is spinning at quite a high RPM, and then it's transmitting a lot of motion and slowing this way down. One of the hobbies that I have is model railroading, and our little scale engines have electric motors in here that spin really fast, and we use worm and gears to slow that down. Otherwise, our little model trains would go at about a scale speed of 500 miles an hour, and they'd never take the curves, and it'd be a lot of other different stuff going on in there. And we use worm gears a lot. Basically, it's kind of at an angle a lot of times, just because there's not very much room. So other little models probably use that. I don't know if they use them in slot car. Do they even do slot car racing anymore? We used to do that years ago. Okay, I'm dating myself.
RC cars.
It's all RC cars now. Yeah, well, we used to have trots, you know what I mean?
Now they raise drones.
Yeah, right. And then helical gears, quieter and more efficient than normal spur gears. Have their teeth cut at an angle across the gear wheel. Each tooth is slightly curved so that it forms part of a spiral or helix. Helical gears found in car and motorcycle gearboxes where smooth, quiet, high-speed transfer power is required, and other examples as well. All right.
Oh, question.
Yes.
Is there any reason not to use helical gears? Like, why aren't all gears helical?
That's a very good question, and I don't know the answer.
Cost.
Price. That's what it is.
Probably price.
Manufacturers.
Yeah.
There's no
And
other reason but price.
some designs just don't need that added expense.
Yeah.
You could probably buy just a regular gear a lot easier than you could buy a helical gear. And you probably get looking at more custom made would be possibly my guess. Because I have to answer something. All right, the assignment itself. Whoop, I didn't mean to do that. I meant to go back up here to the content tab. When you get to the content tab in D2L, there's the module assignment number 6. Those of you that are really astute have realized that we're not doing any assignment 5. Because I didn't want to renumber everything, and there was an assignment 5, but it got taken out a while back. All right, so assignment number 6, working gear. Number 1 is the document that you're going to pull up. It does replicate what's in the textbook, but there's a section in chapter 20, gear drives, Pay particular attention to the example of a working drawing. I will show you that in just a minute of a spur gear. And then the assignment itself, make a working drawing for gear number 1 based on the information in the chart shown for a single spur gear. Include in your drawing the cutting data chart per the example that's shown on page 26, as well as the example drawing included on D2L in the content module. Title of the drawing is Working Drawing Gear Number 1. The text height of that will be 3/32 of an inch. The drawing number is KIN 255-6. Text height 1/8 of an inch. Material is MI, and I've done some research and I don't really know exactly what MI stands for. I have not been able to find it out. But it's in the text, and that's the material that we're going to use.
Machine identical.
Mild iron, I don't really know. I mean, I haven't been able to find it in my list of normal type abbreviations. That height is going to be 1/8 of an inch.
Machine iron.
The drawing scale is full. Text height would either be 1/8 of an inch or 3/32. This is pretty standard height of titles and drawing numbers that you've done so far. And then, of course, your name and the date. That's 3/64 of an inch height text. Okay. I am only asking for an electronic copy of the drawing. I don't need you to print that out. I'm hoping that it won't take me too long to correct them. What I'm really hopeful of is the fact that I'm giving you enough information that there should be no omissions or things that are done wrong height-wise. You know, text height is 1/8 of an inch. Or, I mean, the note text height is 1/8, and all the rest of the text is going to be 0.1 unless noted. You can do the electronic submission through D2L on the assignment tab in there, or if you're on campus and you want to drop it off electronically outside of D2L, then I'll show you this. But on the desktop, there's a classroom files folder. And then when you click on that, up pops the Cadd folder. You click on that and you get into Cadd 255 kinematics drafting folder. Project files folder. Oops, too much cutting and pasting here and forgetting. That should be Tuesday, Thursday folder in there, sorry. And then you're gonna have your name folder in there. Too many, two classes that are too much the same. Back to content. Then there is a PDF of what the drawing should look like that will come up, and I'll explain that with the drawing in AutoCAD. There's also going to be the sample drawing up here on the whiteboard that will be available to you. It's not very complicated. It should be very easy. And then, just in case, I put in a B-size download AutoCAD drawing that you can use for your title block. Just trying to cover all the bases. All right, the drawing itself. Let's go here. Let me switch over to... So this is part of what you should probably read through. Chapter 20, Section 3 that talks about gear drives. I'm not going to read through all of that. It shows you some. What you need to know is that there are it's something called a tooth form or pressure angle in defining different gear forms. And what it is the 14.5 degree pressure angle or tooth form has been used for many years and remains useful for duplication or replacement of gearing. Standard angles of 20 degrees and 25 degrees have become standard for new gearing because of smoother and quieter running characteristics, greater load carrying ability, and fewer number of teeth affected by undercutting. There are some minimums in the number of teeth that need to be included in a design. You can read that and look at that. And then there's some gear terminology in here that you will be using when you get to The formula, of course, there has to be a little math involved in here. The formula and how to calculate some of the sizes that you would specify for a particular gear. There's something called a chordal addendum. There's a root diameter, there's a pitch diameter, there's an outside diameter. There is a hole depth, which is basically the height of the tooth itself. There's an addendum, a dedendum, a chordal thickness, a circular thickness, circular pitch, and face width. These terminologies, just acquaint yourself with them, are going to come into more practicality when I talk about you developing the 3D model of a gear in SOLIDWORKS or Inventor. Then you really need to be much more concerned about those from a dimensional standpoint in your developing your tooth profile and then arraying that. And then the face width would be just the thickness of it. Now, to accurately draw a tooth form takes a lot of time and effort. So we do basically an approximation of what the tooth looks like. If I'm specifying a gear with a number of teeth, as a drafter, I'm most likely going to a catalog, working with a supervisor, engineer, or supervisor person as an entry-level drafter. I'm not probably drawing a gear specifically like what you're going to do. And when you get to that point, the drawing itself becomes very simplistic. If the front view is included, which in your particular assignment is not going to be included, we're just going to do a section view in here. The outside diameter and the pitch diameter and circular pitch a lot of times are just shown as a phantom type line or a hidden line. And what's included is the cutting data, which could include the number of teeth, the pitch diameter, diametral pitch, pressure angle, hole depth, chordal addendum, chordal thickness, circular thickness, and working depth. That's all the information that a machinist would need to go get his cutters, or her cutters, as the case may be, and cut the tooth form correctly. So as a drafter, we're going to include that. On your drafting assignment and on the sample drawing, the calculations have already been done as the sample. So you look at them and go, okay, my work's already done. No. You are going to go through the formulas and you are going to hand in an additional sheet of doing the calculations of the formula to make sure that these numbers are correct. You never know what Mr. Truman will throw out there on a drawing. They might be correct, they might not be correct. And you need to go through the formulas and do the calculations to verify that those numbers are correct, or to do the verification process of learning how to use the formulas. The formulas themselves are really fun. You need at least the practice of doing the formulas, because you are then going to do all that formula calculations in mathematics when you get to the creating of the 3D solid model next week. It's not
24 in the textbook.
It's page 24. That is correct. Not all of these formulas are necessary for what we're going to be doing. There are 2 columns in here. Let's see if I can get it even a little better. That's a little better. All right. The first column over here is for metric gears, and over here is the inch column, so we're going to be using that. One of the pieces of information that you're going to need is the number of teeth. In the problem, in the textbook, you are given the pitch diameter and you're given the diametral pitch. The diametral pitch is a ratio equal to the number of teeth on a gear for every inch of pitch diameter or circumference. Gears that mesh have to have the same diametral pitch, or they're not going to mesh. They're not going to work. To calculate that, the number of teeth, you take the pitch diameter and multiply it by the diametral pitch. Pretty simple. One other aspect that you're going to need, you'll need to calculate the addendum, because the addendum gets used in another formula that's down a little further. The addendum becomes if it's a 14.5 degree or a 20 degree, the addendum is equal to 1 divided by the dimetral pitch. They're fairly easy formulas to calculate. You basically go, oh, this is the information that I need, I'm going to plug it into the formula and come up with an answer. The hole depth, which is the height of the tooth, yes, Pierce?
So I remember you saying that, or maybe it was the presentation earlier, but like 14.5 and then like 20 to 22 are like common angles for
Right.
these. Okay.
You could see a 14.5
Okay.
degree tooth form or pressure angle,
Okay.
or 20.
So we're not going to see some weird number.
No, you shouldn't see a
Okay.
weird. It's standardized.
Cool.
That the design has been worked on and works out for the standard sizes.
Cool. Thanks.
Okay, the hole depth. For 14.5 or 20, the hole depth is equal to 2.157 divided by the dimetral pitch. So they're pretty standard, pretty easy to do. Don't really need the outside diameter, don't need clearance right now, don't need base circle. There's just a couple of things, but what you're gonna do is calculate and verify the circular pitch, the chordal addendum, I think, and the working depth. I'll have to look at the drawing. But like the circular pitch is 3.1416 times the pitch diameter divided by n, which is the number of teeth, or you could use 3.1416 divided by the dimetral pitch. Either this one or this one would give you the circular pitch. The formula to be aware of and careful about is the chordal addendum. The chordal addendum, also known as the corrected addendum, is the perpendicular distance from the chord to the outside circumference of the gear. It uses the addendum, which is calculated up higher in the chart, plus T, which is the thickness, the circular thickness, which you'll have to calculate. You can use either this formula or you can use this formula down here. If you did this one and this one, you would get exactly the same number at the end. So it doesn't really matter. But you need T. This is really hard to see in the formula in the book. That is squared. There is an exponent of 2 right here. So it's T squared plus 4 times the pitch diameter. You just need to be aware of that. It's a little bit difficult when it reproduces. Actually, didn't even think of this yesterday. But oop, need to slide that over just a little bit. There's the formula right there. It's squared. And in reproducing and making the publication on that, so you see that it's got T squared divided by, what's divided by, not plus, 4 pitch diameter. Your formulas in your textbook should show up, you know, a little clearer than that, but just be careful of that. All right, that means that in the drawing. Now in your sample drawing and the one up on the board, in previous classes I have said you might want to consider making a table out of it, an AutoCAD table for practice. I'm not a huge fan of tables. It's kind of cumbersome and you have to do a lot of tweaking to it to get the fact that you suppress the leading 0 and you get the right number of precision numbers in there. You could just do geometry. You can do lines and create lines to create a chart and put it on your drawing. If you wanna go that route, I've given you the dimensions, basically the dimensions that chart should end up being. It does not have to be exactly 3.95. You could actually make this 4 inches if you really wanted to. And you can leave off this last line if you want to. Or you can do it as a table. It doesn't really matter to me. So I've given you 2.75, and this could be even 2 right here instead of 1.98. It's just the size, because I did make this out of a table in AutoCAD. Then this height up here is 0.12 and centered, and then 0.10 for all the rest of this text height in here. 0.35 TYP means typical, which means 0.35, 0.35, 0.35, 0.35, 0.35. And the height typical would mean that includes all of those as height. So you can just draw it, put text in there, multi-line text, or you can create a table. It doesn't matter to me.
To start, is there a piece of information up there that is correct that we can start working our formulas off of, or?
Well, the little secret is that all of those numbers are correct.
Fair enough. But you want to see us do the formula?
I want you to prove that they are correct
Okay.
by doing the formulas. I gave you what it should be. That's kind of better than you actually doing it all on your own and not really knowing what it's supposed to be. Eric?
These formulas, can we do it by hand and then turn it as a PDF?
Yes.
Okay.
You could do it as a PDF. You could do it as a Word file. There's another assignment heading that says Assignment 6 Calculations. Yeah, you can do a PDF and upload it up into D2L. You could even hand it in to me in person if you want to. And I'm basically just going to try to check these drawings electronically to kind of cut down a little bit on the paper aspect of it and try to make it a little faster. Again, it better be right. When we're halfway through this term, and you've had some of you've had me for intermediate drafting and know my standards of height of text and the fact that it's Arial font, bold font style. So, but electronically, they're not so big that I can't check that really quick and add a note to your drawing. If for some strange odd reason that you didn't do it correctly. And you are going to draw this section view. Now, the hole depth, or the working depth right over here, the hole depth is 0.431. That is the distance from the outer diameter down to here. That is your distance right there. Pretty much everything else has dimensions on it. And information that comes from the textbook or the handout sheet itself. So use good dimensioning skills. Don't forget your diameters in here. You're going to have to add the diameter symbol because this is a linear dimension. You need the %C. That drives me crazy as much as anything else that you don't, because those are diameters on there. A simple note on here, 0.25 by 0.125 keyway. 0.1 in your dimension style. You've got dimension style requirements sheet that you should go to. There's a note down here. The height of this text for notes is 0.12 or 0.13 if you're using 2 decimal places. Underline. And then this height of this text down here is 0.1. That's pretty standard for any kind of a notation. Generally, the note is in the lower left corner of the drawing, not out here somewhere floating around in space. A couple of center lines, because it's a cylindrical shape, that kind of stuff. Pretty simple, drafting fundamental, intermediate drafting kind of stuff. Any questions? By the end of class on Thursday. Most of you will get this done pretty quickly. All right.
Which Thursday?
the 4th of May.
In case you know.